Yeah. So yeah. Um, so let's start. I hope I am audible. Uh, so today's discussion is on the this is like the last class. Yeah. So this is like the last class on metal casting topic of our syllabus. We spent around 4 classes, 4 weeks, and around 20 classes on metal casting process and various aspects of it. So today's discussion is also more on theory-based kind of discussion. Previous class was more on numericals based, but this week it's more or less again going back to the theory part of it. And if you have gone through the lectures that were taught by professor during the course of this week, which is week 4. In first week, we discussed about various type of furnaces and other things, and then next class was on various concentrations during the casting of cast irons, and next it was on regarding uh, non-ferrous castings and steel. So what are various casting considerations that we need to consider when you do casting of steel and non-ferrous metals. And then next one was regarding casting design considerations. So it's like a broader, not particular to any type of class of metals or alloys. It is broader consideration that it's like a summary of what we are discussing so far. So basically, if you have a job, so you have to do some casting, and you have to, and you don't know anything. Basically, you have to start from scratch. So in that case, what to do? So it's like a general procedure that you should follow, because there are many things, not only like material, which material you want to cast, etc., but there are many other things which contribute to the good casting products, and what all those things we'll also discuss today. And finally, we concluded with the important discussion on casting defects. So, you know, uh, whatever you do in real life, there will be always some defects, and you know, because nothing is perfect. I mean, on pen and paper, you can solve any equation or any process. You can model it or idealize with some assumptions, etc. But in reality, because of many uncertainties and unknowns, as well as variations in your manufacturing processes, there will be some defects. But our objective is always to minimize the defects and to increase the productivity or casting yield of the process. So, there are certain defects which are well studied and well uh, known, and how to tackle them, what should be done. So those things are also discussed in the last week's, last class of this fourth week. Okay, so this was a broader uh, overview, and with that we'll start. So we'll discuss. As you may not now be aware that we don't just take problems or numericals because there is no context without discussion on how we arrive on those things. So far we have seen that we discuss one by one what all concepts were discussed in the last class or the last week's content, and then we try to solve some problems along the way. Okay, so first week was regarding the furnaces, right? Okay, so see this furnace topic. If you are, I mean, 1 second. So if you are preparing for some competitive exam like GATE or something like that, the furnaces topic is not that important for GATE exam. But if you are preparing for some exams like engineering services or civil services, mechanical or production engineering as options, then we should study this furnaces topic also, because sometimes they'll just randomly ask about some furnace to mention the working principle, the advantage or disadvantage, or some key things about these type of furnaces. So yeah, that's why you should study these. And if you are not convinced with the material that was taught to you in the class, you can Google or do online search or chat GPT it. There is a lot of information available nowadays. Okay, so it's not like there is limitation to the sources of knowledge. It's just that it depends on how creative you are or how hungry you are to know things. Okay, so I'm just looking at previous year questions and trying to see that if any such thing is asked, because numerical part we already did. Yeah, so these casting defects are asked many times. Other than that, yeah, I mean, casting defects are important if you are preparing for some competitive exams, because I'm seeing many questions on that. Okay. Yeah, one second, I'll just look for any other questions are there. Yeah. So anyway, let's start. So I mean, we already started, but yeah. So let's start particularly with the furnaces. Okay. So there are many types of furnaces. So in our class, somewhere introduced, it's not like only those are the types of furnaces that are available. There are many furnaces, but the ones that were discussed in the class, they are like the you know uh, mostly used kind of things, widely used kind of furnaces. Uh, and if you ask, the first question that should come to your mind is, what are the furnaces? I mean, what is a furnace? So basically, you have an like metal ore or something like that. It's not in pure form. Okay. Anyway, uh, nowhere you'll observe that it's in a pure form. So uh, to make any kind of pure metal or alloy kind of uh, material, first you need to melt the naturally formed ore, and to do that we use furnaces. So basically, furnaces are devices operating at typically higher pressure than the melting pressure of the concerned material. And you know this is very widely used technique. I mean, the furnaces are very widely used. It's not only uh, uh, I mean, it's not limited to particular class of the uh, materials. It's not like only materials, only metals are like that. Many a times polymers, etc., are also used, I mean, are melted using furnaces. Okay, so, so if you want to, general classification, if you want to look at, so, you know, so furnaces are typically classified into two types. One second. Yeah, first are called as fuel fired furnaces, and nowadays these electric furnaces are also quite popular. So, as the name suggests, fuel fired furnaces use certain sort of fuel, and when you burn the fuel, you get the heat output, and that heat is used either directly or indirectly to heat the ore, metallic ore, or anything that you want to purify or melt. Okay, so there also subcategories are there. Some are coal fired. These were initially quite popular. Initially, I mean, like few decades back, because of you know lesser environmental awareness and easier availability of coal, and other components are also designed for coal fired, because after industrial revolution, this when steam power plants, etc., steam engines, etc., came up, they were all based on coal type of fuels. And then later on, this diesel auto, this petrol, diesel, etc., came up. Nowadays, even more things have come up, like natural gas, compressed natural gas, producer gas, hydrogen, methane. So, things are evolving, but still, coal is like the primary source of fuel in combustion kind of arrangements. Okay, so coal fired are there, then oil fired are also there, and then you have gas fired. So, depending on what type of fuel that you use, they are classified. Then, in coal fired also there are certain major categories. One is called cupola furnace. Then there are some rotary furnaces and some pit furnaces. Okay, so this is a general classification. It's not like there are only these three. There are more than these three, but these three are like prominent ones. Okay, and then in electrical, so you can have multiple classifications. One is like electric arc furnace. Then you have induction furnace, electric induction furnace, and sometimes they use electric resistance heating also. Okay, so these are some categories in the furnaces based on electricity. Okay, so this is your you know broad this thing. And nowadays, as I said, coal-fired ones typically we try to not rely on them much because of environmental concerns and regulations. But still, many places you'll see coal-fired ones. Okay, it's not like they are out of out of fashion or something. Very well used nowadays also. Nowadays they are quite refined also. I mean, there are like fluidized, etc. Those kind of combustion techniques are there. Then you have uh, like when you release the combustion products, you'll have uh, devices like catalytic converters, or some arresters are there who, like, those devices, you know uh, does not let harmful gases, I mean, within certain limits, to go out with the flue gases, etc. So many more things are there, but that's not part of our discussion. But yeah, the point is nowadays also coal is quite used. Okay, and there is another classification, like in case of coal fire things, uh, there are, I mean, depending on where you want to use it, like you have subcritical things, supercritical, etc. So there also coal fire furnaces are used. Okay, even in India, I mean, we are trying to move towards uh, renewable energy sources, but at this point also I think more than 50% energy is produced from coal. Okay, the reason is pretty simple. I mean, it is a reliable technique, very well studied and very well used. So many decades we are using it. Affordable, abundant coal. In Indian context, our coal is slightly of lesser quality, but yeah, in many countries or many continents, very high grade coal is available. So you know that makes the prices lower there, and it's very well competitive with other sources. And yeah, the main thing with the coal is the environmental concerns, greenhouse gas emissions, uh, you know, uh, global warming. Uh, but when you mine the coal, also there is some concerns there, such as destruction of natural habitat due to mining, etc. Those things are there. Plus, you know, there is a problem of waste also. When coal is burnt, you end up with soot, or I mean, other than the flue gases, you end up with some soot particles, etc. So disposing that is also a big challenge. Okay, so let's move forward. Let's go to the first type of furnace that we are supposed to know, which is cupola furnace. Sometimes they are called as cupola also, so it doesn't matter. It's a pronunciation choice. So first of all, you should remember why. I mean, what is this? So this is primarily used for uh, melting or cast irons. So from iron ore. Okay, so I'll just give you the whole thing. Yeah, so primarily used for producing cast iron. Okay, so this is also very important question. You produce cast iron using cupola furnaces. Okay, primarily. So what happens? Basically you have a pig iron. So the natural iron that you get from mining is called as pig iron. This is your ore, whatever we call. And then uh, 1 second. Yeah, sorry. Uh, this iron oxide or iron ore, we use blast furnace to convert it into the pig iron, and then we used cupola to convert this into cast iron. Okay, so this is the sequence. uh, Pig iron is like the soft and ductile kind of material, so it's like the uh, purest form of iron. Okay, so and then what happens in cupola? You carbon load it. You put basically you want to include carbon to give it strength, etc. Various properties depending on carbon concentration. So here carbon concentration is like greater than 2% usually in cast irons. You should note that. I mean, if you have studied your material science iron carbide diagram, maximum solubility of carbon in iron is 6.67 percentage. Okay, so you cannot, I mean, even in solid state, uh, when it solidifies, it cannot uh, contain more than 6.67% of carbon. Okay, and if it is less than 2%, we call them steel. So those kind of iron plus carbon products, we call those steel. and if it is greater than 2%, the carbon concentration, uh, it is called as cast irons. This is basic, this thing. And what happens when you have a purest form of iron? So typically you'll have like 98.7% of iron in this. So there are some impurities. It's not like it's 100% iron, but mostly it's iron. Purest form that you get is pig iron. This number can be different. Different depending on what book you follow, etc. But then in cupola, you'll see, we have something called as charge. Uh, you know, so charge in cupola furnace is nothing but you know it's a mixture. It's a mixture of pig iron plus flux plus coke. It's layered mixture, and flux is most of the time limestone, etc. And the use of flux, or the objective of the flux, is to uh, uh, you know what happens if you don't put flux. This coke and pig iron, etc., whenever this melting process happens, there are obviously some impurities or byproducts that are formed. But when you mix it with flux, what happens? This flux also contributes to impurities, but those impurities tend to be lighter than the cast iron. So basically, they float on top of your cast iron liquid, and that's easy to separate. Okay, so that's why flux is put. Okay, and sometimes it avoids like direct contact of coke with the ore also, because sometimes what happens, then your carbon concentration will be very high if it is direct mixing like that. So that's why sometimes flux is put. Most of the time flux is put. Okay, so the advantage of cupola furnace is that you know uh, it is you know uh, it is good for cupola furnace is suitable for large scale productions. Okay, so it's not for a small scale. So it's like 8 to 10 tons per cycle. So once you charge the cupola, and it's not like you put like 10 kgs or 20 kgs of charge. It's very big. So that's why. And there is one version of this which is called as uh, hot blast cupola. So what they do basically is you know the flue gases, the combustion flue gases are reused to preheat the incoming fresh air for combustion. So this is this technique is many times used in not only furnaces but many devices. uh, you'll study those things mostly in power plant engineering, IC engines, or even in refrigeration, etc. You can have reheating, etc. Okay, so those things are there. And you know typically you have temperatures in the range of, I think, 1800 or so degrees Celsius in cupola. So cupolas are not suitable for steel, etc., because you need even higher temperatures. uh, so there electric arc furnaces or electric furnaces are suitable. But for cast iron, etc., this is the best option that you have, and most of the time it is used also. And there is one more thing. Yeah, sometimes nowadays there is something called as cokeless uh, cupola. So you know, basically that they reduce the quantity of coke in the charge, and you know uh, it is replaced with the uh, ceramics or high temperature uh, withstanding materials. Okay, so I think this was discussed in the class also. So here you can use different kind of fuels also, not only coke. uh, you can use other kind of fuels so that you'll have lesser carbon in your flue gases, or lesser. I mean, this is like a environmental friendly version. Environment friendly version of cupola. Okay, so and nothing. I mean, it basically looks same. If you just Google the term, this cokeless cupola, you'll just see that it looks from outside. It looks like normal cupola only, but inside, instead of coke, you'll have uh, this refractory or high temperature withstanding ceramic balls or something like that. Okay, here not necessarily coke. You don't need to use coke. Here you can use any other fuel, and there is burner and those kind of things are there. So it's actually environment friendly version of. So instead of coke, you know high temperature, these things are used. Ceramics, high temperature ceramic is used. Okay, so something like that. So you try to reduce the amount of coke. Sometimes you directly eliminate also. But yeah, since uh, this is the process of making iron into cast iron. You have to provide carbon. So if it, instead of coke, if it is coming from some another fuel which is burning, that is also fine. But it has to be there. Carbon has to be there. Otherwise, it will not make cast irons. Okay, so then there is some term which is called as, one second, charging ratio or something like that. One second. Hmm. Yeah, in cupola, you know, temperatures, maximum temperature is at the bottom. It is, a big column. Uh, if you just Google the image, you'll see it's a big column. Maximum temperature is at the bottom, because there is that is the place where your uh, combustion process starts, and then it goes on heating the those things. So basically, there are different zones. Okay, so if you if you just want to make a sketch, you have, yeah. So you'll have like 5 6 zones. So there is something called as well zone. Basically, this is where you know you collect molten metal and slag. Molten metal plus slag, etc. So because of gravity, it settles down and you collect it from there. Then you have, on top of well zone, you have combustion zone, where your combustion actually starts, and that is where you have like 800 or 850 around temperatures. And then on the top you have reducing zone. So it is reducing because there, you have uh, these things, endothermic reactions involving copper, which comes from the coke, and this carbon monoxide is formed. And then on top of that you have melting zone. So this is where actual melting happens, and uh, you know this thing, what do you say, uh, this iron gets mixed with carbon oxide, and it forms iron carbides, okay, with the release of CO2 gas. Then there is preheating zone, uh, you know because what happens, uh, above melting there will be another charge, right, which is not yet melted, that gets preheated because of melting of the liquid, melting of the iron beneath it. And then above preheating zone, uh, there is something called as stack, or 1 second. uh, 1 second, I had the image of cupola. Hmm. Yeah, so basically, this preheating zone has the charge which is about to melt or not yet melted, and on top of that, these gases will be remaining. So that is called as stack zone, from where it is released to the atmosphere. So these are the important uh, you know uh, zones. So there are many things that go on, and basically, in preheating zone, you feed the charge from here. There will be one door to feed the charge, and then at the bottom you take away whenever it is melting. Okay, so these kind of things are there. There are many reactions that take place simultaneously, so I'm not going into those details. But motamoti, or broadly, this is what you know. These are various cupola zones. Okay, so it's not like one step process. It's not like you put the charge and it just melts. It's not like that. It takes some time. Okay, and there is something called as charging ratio. Uh, you know, is sometimes they ask uh, this also in competitive exams. So for cupola, there is something called as charging ratio. If you don't know the term, that's when the problem comes. But if you know what it means, it's not that big of a deal. It's nothing but a ratio of uh, metal to coke in the charge. Okay, so how much charge? See, as I told, in charge you'll have coke, limestone, and metallic ore, right? So how much metal you put uh, per kg, in terms of mass to mass basis, that is what it is called. And typically this value, it changes. It's not a constant value, but broadly speaking, it should be within the range of 6 is to 1 to 12 is to 1. Okay, so this is like the range for optimum charging ratio. So if you have like 6 tons of metal, you need to use 1 ton of coke in the charge, like that. So, and then you have some correlations for how much line or flux to use. Those things are also there, but this is important ratio, charging ratio. Okay. What else is there? Let me just see if I missed something about cupola. Yeah, yeah. And sometimes to reduce the um, what happens, these temperatures are pretty high, right? So the refractory lining, which is inside the furnace wall, uh, it sometimes get damaged pretty easily or more frequently, because even refractory materials have some working life, and therefore sometimes they are water cooled also. The refractory walls of the furnace, that is called as water cooled cupola. Okay, and sometimes you, depending on the nature, the pH values inside the furnace, if it is acidic, you have to put some basic linings on the refractory and vice versa. And yeah, there are then other things, etc. But this is like the most common aspect for our competitive exam preparation. Other than that, yeah, I think we covered most of the cupola. So let's move on to the next one, which is, yeah, and as I said in the classification some time back, yeah. So this is one. So then you have rotary furnace. See, it's nothing different. As the name suggests, it's basically cupola, which is keep on rotating. Uh, but it's, I mean, it's not strictly cupola, but because it is, see, you cannot have this much high temperatures and keep on rotating those things. So basically, uh, these rotary furnaces, they are used for aluminum scrap or any other scrap. These are like recycling furnaces. So whatever scrap you see many times, you see some people picking up the scrap in the scrap yards, etc., right? So they take it to recycling, and mostly there will be rotary furnace there, because uh, basically the scrap is put from the top. It is a slanted furnace and it keeps on rotating, so this mixing etc. is pretty good in case of rotary furnace. And you know it's not only for aluminium, you can use for iron, titanium, etc. It depends on what you want to use it. Okay, then the pit furnace, it's like a smaller cupola kind of. It's a small furnace, and it's fast, it needs lesser space, and it's cheap also because it's small. It's not the size of cupolas, it's a smaller one, that's why it is called as pit one. Working principle is more or less same, but the orientation and the size, etc., those things change in these guys. And then in oil fired uh, cases, wherever you have availability of such oils or those kind of natural resources, you can use those. Especially nowadays, this biodiesel, etc., is coming up instead of petrol or diesel. So biodiesel blends are also very important. And in gas fired, as you know, it's natural gas or methane, propane, butane, whatever gas you have available. But it has to be cheaper. Otherwise, there is no point, right? Who will pay that much cost for just melting? Economically not feasible if you use propane or something like that. Mostly natural gas, producer gas, biogas, those things are used. Working principle is more or less same. Okay, so then what else is there after cupola? Which one was the next in the class? Let me just see. Yeah, crucible. Okay, so the next category is crucible furnace. Okay, as the name suggests, it is uh, uh, it's a small scale. It's not as big as cupolas. That is first thing. Maybe I'll write it here. Not big as cupola. Okay, and what is, I mean, this thing, there are different types. Again, here also you can have coke fired, oil or gas fired, etc. Because combustion process is the change, right? It's in crucible you have a small ladle kind of metal, and it's a small scale. But the combustion process or the working principle is more or less same, and the core of it, you melting something using combustion products, but at a small scale. That is what crucible is. Okay. uh, and one more thing about crucibles is, one second. Yeah. So last one in crucible, right? One second. Yeah. So you know, I mean, what happens? You have some ladle kind of thing. So here you put your charge. Typically, here the advantage is, what happens here, and you'll have some refractory lining, etc., because very hot gases will flow around your ladle. So something like this. I'm just drawing it simply. And what happens? So this is your refractory lining or wall, you want to call, whatever it is. And then what happens once the combustion starts? The combustion products, let's say you use some blower, etc., they come here and they go around your ladle, and then they go out. Okay, so like that. So this is your combustion products. So the thing is, in crucible kind of furnaces, you know, as you can guess, there is no direct contact of combustion products with the metal that is melting or ore that is melting inside the ladle. I think it is double D. Okay, so no direct contact with melting ore, or maybe I should write between melting ore and this guy, combustion products. Okay, and typically these are better for lower temperature melting alloys. Uh, you know, so useful for low temperature or low melting point materials. Or most of the time it's metals, but let's say materials such as aluminium, bronze, brass, etc. Okay, so the disadvantage here is, you know, what happens this when you melt this ladle and take it out for pouring in your casting mold or somewhere. Uh, you have to be careful. Uh, you know, careful while transferring the molten metal. I mean, you get the point, right? Because since it's a ladle, there will be significant heat loss when you take it out from the refractory or your furnace. So you have to be careful. What happens? Sometimes the solidification may start in your ladle only. Okay, so those things you have to take care of. But yeah, advantages are like it is like easy to maintain, low losses, etc. You know, environment friendly as compared to cupola, etc. Okay, yeah. So That's most of the things about crucible furnaces. Then next one was open hearth, right? Uh, See, the open hearth and all these are like big kind of furnaces, not vertically but horizontally kind of. These are used, so like in the factory shop floor, etc. You have uh, you know production lines, right? So these lines uh, keep on, like these are big long lines, right? So here also in open hearth, etc., it's like that only. Okay. 1 second. I just saw about this, but I forgot where did I see open hearth kind of thing. I think it was a book. 1 second. Somewhere here I saw. Yeah, they are used for steel, etc. These earth ones, because you can go up to very high temperatures also here. Because the thing is, uh, combustion takes place somewhere else. It's not within the where the charge is kept. So you can use multiple these things, you know, combustion sources, etc. Okay. So if you just see the diagram, you'll understand what I'm saying. The diagram that was shown in the class, it was a side like cut section view. But if you see a 3D diagram, you'll understand what it means. Okay, I'm not able to show it here, but you get the point, right? So, and the advantage is it can be used for reusing the scrap, etc. Uh, Disadvantage is it is not small. Okay, uh, it is like cupola kind of thing only. Uh, it's slow. It is very slow process. Uh, you know, but advantage is again I said that you know. 1 second, I'll just give you the total answer once. Hmm. It is also called as Siemens-Martin process. Yeah, sometimes they call that also. Okay. It's a slow process, so you can have better control, and the slag formation is less. Overall efficiency is better. You know, but yeah, that slowness can be also considered as the uh, limitation, because you cannot have rapid or faster kind of productions here. Uh, you know, but yeah, it is mostly used for high quality steel kind of things. So open hearth, these things are important for steel production, not like cast iron, etc. Those things are not important here, because the flue gases, etc., flow on the top of your charge. They usually don't mix with your charge, but since it's a direct contact thing, it's efficient. Okay, yeah. So we'll not go into details, because it will take some time and not good for our discussion. It's not relevant that much. Then there are different kinds like reverberatory, etc., etc. You can just Google them. Uh, but apart from this, then the electric ones are the important. Okay, because nowadays we are mostly shifting toward you know electric kind of furnaces. So you know, this electric arc furnace, we saw some classification, right? In electric case, electric arc, induction, resistance, etc. are there. So in electric arc, oh, sorry. Okay, so these are also can be used for you know higher temperature metals, higher high melting point metals, okay, such as steel, etc. is also possible to melt using electric arc furnaces. Two types are there. You know, uh, first is called as non-consumable electrode, and then obviously there is second which is called as consumable electrode. So I hope you guys know what is the principle behind electric arc furnace. I mean, it is the same principle which is used in our starters, bike starters or car starters, etc. Whenever you have electrodes not connected but very well, I mean, the distance between them is very small, and if you apply high voltage across those voltage those electrodes, the air between the electrodes get ionized, and there is a you know, large amount of energy release in a very short span of time, which typically causes sparks. Okay, so in our starters, we use that kind of logic. And here also in electric arc furnaces, we use the same thing because these sparks are very high temperature releases at shorter time durations, and you can use those to melt metals. Okay, so that is the basic principle. We'll see such kind of things in metal arc welding also later on, but the principle remains same. The main advantage is here no coke or combustion fuel required. Okay, so then these becomes environmentally friendly. But see the it's if you want to you know uh, say that, you can say that, but at the end of the day, the electricity that you get, you know, it's also not uh, pollution free, right? I mean, uh, you get the point, right? I mean, electricity is also not uh, environment friendly production always. So you have to think of it in that sense also. Sometimes they have another classification which is direct arc furnaces, indirect arc furnaces, etc. So as the name suggests, indirect arc furnaces, uh, you know, you will have your ore surrounding the electrodes and then you start the arcing process. But in indirect, what happens? They rely on the radiation heat transfer between your arc and the metal. So it's not a direct contact; it's indirect contact. But I mean, it's not that big of a deal. Okay. So and sometimes what happens? This electric arc, etc. It's a noisy process. Okay, so that's also one of the disadvantages that this is not a quiet operation. So that's where this you know induction furnaces come into picture because these are pretty quiet electric induction furnaces, and they are also widely used, these induction furnaces, uh, and they work on the principle of magnetic induction, electromagnetic induction. So when a current flows through a coil which is wrapped around some core, and you have another coil which is nearby, so those things are there, right? So based on that principles, we have electric induction furnaces. uh, yeah, this is noisy, these are quiet. they work on the principle of magnetic induction, right? And they are suitable for all types of materials. Okay, so it doesn't matter if it's a steel or iron or whatever it is. They are quite versatile in the operation. Okay, and there is no contamination, etc. I mean, it's a property of electrical furnaces that there won't be any contamination to the charge, because there is no combustion, etc. happening inside. Okay, so then there are some classifications, etc., but not that important. Uh, Let me just see some advantages. Something like that is there. Yeah. So advantages are like quiet, energy efficient, clean, less pollution, etc. Uh, and the disadvantages. Hmm, yeah, I mean, there are not much disadvantages, uh, because if depending on how much carbon percentage you want, you put that much in your charge. So this is basically all materials that I mean for ferrous plus non-ferrous. Okay, so that's what typically means. Okay, and yeah, one thing before we this charging ratio is also called as melting ratio. Some places. Okay, and instead of 6 to 1, you can take some broader number, because otherwise you may not. In some cases they write 4 to 12 also. Just for the sake of argument, you take that. If it is 10 to 1, then that's more practical number. Okay. So with this, I think furnaces is complete. I mean, it's more of a theoretical discussion. There is not much in the context of numericals here. So let me just see your assignment and see if you can answer those questions. Yeah, one question on cupola, crucible. Yeah. So yeah, I think we have discussed more than required, I think, on this topic. Let me just see one more thing. Any other questions are there? Yeah, in cupola, as I said, you can melt cast iron, but you can't melt steel. Okay, so that is a limitation of cupola. Keep that in mind. Mm, yeah, so let's move on to the next part. So there were a couple of classes in which uh, those things are discussed. Okay, for cast iron, etc., what to do, and those things. I mean, you can go through that, but it's very theoretical thing. Uh, I mean, uh, you know, to be honest, I also don't remember these things, so we have to keep on revising, etc. But basically, you need to remember, in cast iron there are different types. Okay, so let me just give you a brief idea about those things. Furnaces we did. Now we are into cast irons, right? Yeah. So yeah. So one second. Yeah, there are steels and then there are cast irons. So in cast irons, there are different categories such as grey cast iron, white cast iron, malleable cast iron, ductile or spherical graphite or nodular cast iron. You know, so grey cast iron, it basically has flakes of graphite. So some points I'll give you because this composition etc. you can read it on your own because I mean it's all theory. You cannot remember those things. You have to, and in many competitive exams they are not asked also. So don't worry. But some things are there that you should remember. So if you consider cast iron, there are different types. First is grey cast iron. The thing that you should remember about grey cast iron is you'll have flaky graphite, you know, inside. So the carbon that is in the graphite, flaky graphite form. So basically like this. So it's not a nodular or anything. It's a flakes, and therefore it is poor ductile strength, strength or ductility sometimes they call it, but very good damping or compressible strength. Okay, so if you have seen your lathe machines etc., sometimes the bottom is made up of uh, grey cast iron because it is very good damper. Okay, its compressive strength is very good but the ductile strength is poor. Okay, and there is one more. uh, yeah. Sometimes they ask that is cast iron, it is easier to machine than steel. Okay, plus lower melting point than steel. Okay, so these two things you need to remember about cast irons in general, and then we are talking about different types of cast irons. Uh, so grey cast iron is there. Okay, okay. Then there is something called as white cast iron, and see the name, they give these names based on when you cut this cast iron freshly, how does that surface appear. So if it is appearing in a gray color, it is gray. If it is appearing whitish, it is white. Okay, so then there is white cast iron. And instead of graphite, okay, so we are talking about these, right? So next category will be white cast iron. So instead of graphite, you will have cementite and perlite. So the carbon will be present in this form, and this white cast iron is very hard, so it has a high hardness, and it is uh, abrasion resistant. Okay, and this is hard, and that's why sometimes they are used at high temperatures also to maintain hardness. White cast iron can be used, and it also has a high compressive strength. Not damping, but compression is okay. It is possible here also, as same case in the Greek cast iron. Yeah, and since it's hard, it's difficult to machine. Okay. In general, as compared to steel, cast irons are machinable, but uh, there also it depends, right? How easy it is or how difficult it is. Okay. Then the next is malleable cast iron. And what they typically do is, as it says, sometimes we have to improve the ductility of these cast irons. So that's why they make them malleable cast iron. And you know the thing is, here what happens. One second. It has greater ductility than uh, gray and white cast iron. That is first. Mm, and it has you know clusters, nodules, or clusters of carbon. I mean, uh, you know, I mean that carbon can be perlitic or martensitic, ferritic, anything like that. But yeah, it's not a flake, you know, or like that cementite or like that, but it's clustered. Okay, and to do that, they put something in it. Let me just see. Hmm. Okay, so that is in ductile. Okay, yeah. Then there are these different properties, but yeah, this is mainly the thing. If you compare the composition wise, Yeah, it's, I mean, more or less like this only. But then there is fourth one which is important, which is called as ductile or nodular cast iron. And here they use magnesium or these guys, cerium, yttrium for making nodules of, you know, nodules of this thing, what do you call, graphite, nodules of graphite. So here graphite is there, but not in flaky form, it is in nodular form. Okay, and they use magnesium, cerium, or yttrium for those nodular stabilizers. And as the name suggests, it is, advantages. It is uh, this ductile, so we can get maximum ductility in case of uh, cast irons using ductile cast irons. Okay, it will have hot workability, better hot workability and hardenability. Okay, so those things are there because of those modules, etc. Oh, 1 second, sorry, not this. This is for steel, this is not for irons. Okay, so sorry for that. Yeah, but yeah, you can remember these things. This is important for competitive exams. Magnesium, yttrium, or cerium, these kind of components they are added. And yeah, it's like broader classification. You can read more about it in your material science books, etc. But we'll talk about something else which is important from the casting point of view, which is something called as, you know, what is it, carbon equivalent. Okay, so you know this fluidity for cast irons is measured, uh, is measured by this formula. So the unit will be inches here. This will be 14.9 into CE plus zero point 0.5 temperature in degree Fahrenheit minus 155. This is called as carbon equivalent. And it will have some formulas, or it, you have to take percentage of your carbon in your cast iron, then uh, percentage of silicon divided by 4 plus percentage of phosphorus divided by 2. That will be your carbon equivalent, and it should be around 4.55 for maximum fluidity. Okay, so this is the formula that you should remember. Okay, and yeah, I mean, other than that, you know, 1 second. I think there is one question on this in your exam also. I mean, assignment. Yeah. So this is fluidity for cast iron. Okay. So. Hmm, okay. So apart from that, you need to remember one thing instead in case of gray cast iron. This we already talked also previously, that no need of riser, because you know uh, it expands during liquid cooling and solidification, that we already saw, right? When we studied uh, allowances, casting allowances, we had studied grey cast iron as a special case because of this property. But what happens in solid cooling? Uh, you know, solidification, not solidification. Okay, solidification allowance is provided on the pattern. Okay, so main thing is, this is the highlight here, that if you are doing the casting of grey cast iron, you don't need risers because it doesn't need additional liquid metal to compensate for shrinkages. Okay, so that was one thing that is important, and this is only true for uh, grey cast iron. Okay, not all cast irons. Yeah, then uh, yeah, then there is some discussion on steel, non-ferrous castings, etc. Uh, you know, Steel, as I said, it's having higher melting points as compared to cast irons. But there are types also. In steels also there are different types. Okay, so steel, if you want to talk about, but as you said, I mean, less than 2% carbon content, right? That is first definition of steel, and then depending on the content, they divide steel into different categories. Uh, you know, uh, just because of this. So first is low carbon steel, that will have 0.05 to 0.15% carbon. Then you have mild steel, sometimes this is called as MS. It will be having 0.16 to zero point 0.3 kind of carbon percentage. Then you'll have medium steel, 0.3 to zero point 0.6 kind of range. And then high carbon steel. Here also it is medium carbon steel. Okay, so it will be like 0.6 to 1% kind of range. And then you'll have ultra high carbon steel, so it will be like 1 to 2% of that limit. Okay, so what happens as you increase the carbon content in this direction, hardness increases. Okay, so if you have more hardness, this machinability will be less, so all those properties kind of play out. Okay, so uh, low carbon steels, what is their application? Because other ones I remember, low carbon I forgot. 1 second. Yeah, I mean, sometimes they're clubbed with the MS. Okay, so this low carbon and mild steel, most of the times they're clubbed together. They are typically used for these things because they are more ductile, etc. They are used for uh, sheets, etc. Right? Sheets or ductile kind of items or structures. Okay. Medium carbon steels, basically you need more hardness, etc. and strength, good wear resistance, etc. They are typically used in railway tracks. Okay. And this high carbon steel, they are used in dies and cutting tools because they are hard. Okay. And ultra high, they are used in applications like punches, axles, knives, etc. So even harder, and you need abrasive surface, more abrasive surface, then they are used. But in case of steel, the most important ones are alloy steels. Okay, so basically with the carbon, you put different other alloys, and you get different varieties. Most important is stainless steel because of its corrosion resistance. It is very widely used, and it has, like, along with the carbon, it has nickel plus cobalt as alloying elements. I mean, there are other also like molybdenum, etc. But you can think of those things and you can study them separately because we are running out of time. So there are others also. So it's your homework to look for them. I'll just give you some idea. There is something called as tool steel, maraging steel, weathering steel, so many things. Okay, so just have a look. Steel is very important. Stainless steel, though, then there are austenitic steels, and blah blah blah. So many things. But we are dealing with the casting aspects of these. So, since these are high temperature melting point kind of metals or materials, you need to use dry molds, sometimes permanent molds, and ramming have to be very careful. Otherwise, at higher temperatures, if it is not properly rammed, there will be some defect, etc. We'll see certain defects next. So all those things are discussed in the class, and you can uh, look into those. But then what happens when you talk about non-ferrous materials? They are low melting points, and there are special challenges. First is, they have uh, non-uniform chemical composition or segregation, uh, loss by evaporation, air aspiration, and many other things. So those kind of things come into non-ferrous category. So those things are also discussed in the class. You can just have a look. Specifically for copper, it is high conductivity, right? So that's the problem. It solidifies uh, pretty fast because of conductivity, and car- carbon has a higher reactivity with oxygen. So sometimes that also forms carbon oxide, copper oxides, and it depends. The density of copper oxide is, I forgot whether it's more or less, but uh, then you have to choose what type of gating, top gating, bottom gating, all those things. I think for non-ferrous ones, bottom gating is used because of their density of their alloys is uh, more than the uh, pure metal, or yeah, pure metal. Then if it is not a controlled environment, then there is air aspiration, sometimes nitrogen, and some defects will come, etc. So those things are there. And aluminium has also those things. Uh, Aluminum is also very reactive with oxygens. Okay, in the natural form, aluminium is never pure. It is always aluminum oxides and magnesiums, etc. And general considerations for oil casting. Uh, you know, first part is, when you are like general casting considerations. So basically, this is like common sense practices, and first first is uh, you know uh, casting material. So you have to study the casting material, its melting point. If it is alloy, then it will have a range of melting point, etc. Conductivity, density of oxides, uh, fluid life, fluidity, you know, and all those things. And if you want to put some alloying elements, etc., that also you have to take care. Then, second is mold properties. So that includes mold material as well as its making process, etc. You know, depending on type of metal and temperatures that we deal, you need to choose whether you need green mold, dry mold, permanent mold, metal mold, dye mold, whatever it is, and all those things. It has to be, it should have some air vents, riser, all those things. So those we already discussed in previous classes. Those things come under this category. And in the mold also you have to be very careful, because we'll see some defects now. And apart from the characteristic of the material itself, mold also plays very important to avoid the casting defects. Okay, so I'm not going into details because that is already been taught. And some other considerations, like uh, section thickness should be uniform. And what I mean by that is, see, if your final product is something like this, don't make the mold like this. You have to make the mold like this. Okay, like this. And then you do the machining operation after the mold is produced, and then make this. So this is better than this, because if you have thickness changes, etc., there are stress concentrations at the joints, and all those things are there. Okay, and it should be avoided to have a concentration of metal at one place. So you need to, you know, uh, provide some web centerings in staggered manner. Okay, so that hotspot doesn't fall there. Uh, Thin ribs should not be directly joined to the thick ribs, as I shown here, and tolerances, etc. You have to give. These things are pretty common, but many a times people don't follow this. That is the problem. Okay, and always give like chamfers or fillets. Okay, so no need to make the exact part while casting. Just give some allowances, and then you can machine those parts out. Okay, so that is there. And finally, you have to consider economics also, because all these things are energy intensive processes. So you have to consider economics of that also. And then the final topic, which is like the best one, is the casting defects. Okay, and very important as far as competitive exams are concerned, because if you know, then you know. If you don't know, you don't know. It's that kind of thing. Okay, so yeah, so then there is some classification of casting defects. You can define them based on various categories, but most commonly, uh, you know, they are divided into like 4 or 5 categories, such as, let's say, first is gas defects maybe, yeah. So blowholes, okay. and sometimes they are called as open holes also. And you'll see on your casting holes like these, etc. you know that's the problem, because what happens sometimes, there is some gas release when the solidification takes place, because when it is hot liquid there is some dissolved gases, and as the temperature decreases the solubility of gases decreases and they come out. But if there is no proper uh, you know ventilation or vent holes provided in your mold, those things just stay there, those gases, they don't have way to come out, and they cause such uh, these blowholes or open holes, right? And sometimes, this is also called as scars. uh, it's basically shallow glow on the surface. I'm just giving you the names because many a times they just give you the name and you're supposed to know. Then there is something called as blisters. So here what will happen, there will be, okay, so it's not completely open. From the top it will look small, but it is covered hole. Okay, so it's like covered hole. From the surface it will look small, but if you just dig slightly, it will be pretty big just underneath the surface. Then you have pinhole porosity. Sometimes we just call it as porosity. This is primarily due to hydrogen. See, the hydrogen is a lighter gas, so when it comes out, it will not form big holes. It will be small holes. So you'll not be able to see like big open blows or like that. But if you just go close to the surface and try to observe, you'll see big these things. Not big, small size pores. Okay. And how do you prevent these kind of things? Provide proper venting, proper temperature, pouring temperature you need to maintain. Uh, you know, use dry molds instead of green molds, etc. Because sometimes what happens, that moisture also gets trapped. So those things you have to avoid. Then other than that, you have material. Molding material or method defects. Okay, so those include cuts and washes. So cuts and washes. What does it mean? What happens if you have some mold like this? Okay, from here your liquid metal enters, and if it is, the velocity is high or there is a lot of splashing, etc., what happens, your final mold, oh sorry, instead of looking like this, which is the expected one, it will look something like this, and the material on these corners, it will go inside. So material from here will go inside. So that's called as cuts and washes, and it is like inclusions, mostly silicates, SiC. Yeah. Why does this happen? If it is not properly rammed, or if the velocity is too high, inlet velocity, etc., if there is a lot of splashing inside before the solidification, those kind of things happen. Cuts and washes. Okay. Then you know there is again some things called as drop and dirt. what happens if you don't properly ram sand from your cope and drag. For example, you have like this cavity, okay, and this is your cope and drag kind of thing. This is your parting line. What happens? Dirt from here or dirt from like these parts. Uh, this is your cope and drag. So the final cavity that you'll get looks something like this. Okay, it will not look what it looks to needs to look. It will look something like this. So this is called as dirt. This is called as drop. These some names are there. Uh, okay, so you should remember this is happening because of improper ramming or improper mold strength. Then you have something called as scab. So what happens? You'll have this thing instead of scab. Yeah. So oh, sorry. In your cope part, if it is not properly rammed, so what happens? Sometimes if it is not properly rammed, you get something like this, or if it is not properly rammed, what happens? Instead of getting a square or rectangular thing, you get something like this. So your liquid metal pushes to your mold, and you get something like scab. Okay, usually happens in the cop, the top part, because bottom due to gravity etc. It is usually properly rammed, but top part if it is not properly rammed, these scab events happen. Okay. Mm, yeah. Mm. Sometimes what happens if there is a lot of splashing etc. Then also this kind of scab can happen. Okay. Then what do you have? Mm, rat tails, buckles, swell. Okay. So this rat tails. Second. So rat tail is similar to scab, but you'll not have a concentrated uh, extrusion. It's like a long, thin line or ridge on surface of casting. Okay, so you'll not have a concentrated extrusion. You'll have a long, thin lines. So that is called as rat tails because it looks like a tail of a rat. And then you have, I think this swell and scab is similar. Let me just confirm. Swell. Yeah, see, this swell and scab is similar, but swell can happen on any wall. This scab usually happen on the top side, whereas swell can happen on any wall due to uh, pressure from molten metal. So if your uh, what do you call, if your mold doesn't have enough strength, it will just buckle. Not buckle, sorry, it will just deform and it will swell in that direction. Okay, and that is called as swell. Then there is something called as buckle. Yeah, buckle is nothing but severe form of rat tail. Okay, so in rat tail you'll see some uh, lines, but here you can see like lines as well as pyramid shaped bumps or lumps, etc. Okay, or shallow depressions, etc. So it's like a severe form of rat tail. Okay, these are some, like, these are words you don't sometimes know and they directly ask you in the exam. Then there are pouring metal defects. Okay, so far we saw two types. This is third one, pouring metal defects, and very famous two of them are uh, misran. So misran is like if you have a cavity like this, but what happens, the liquid freezes till after reaching this point, so this remains empty. So this is misran. So it can happen a lot because of lot of reason, uh, low fluidity, or the surface structure of your mold, or even surface this mold design, etc. If there is entrapped air, it will try to push. If there is no proper ventilation, all those things are there. That is misrun. Then there is something called as cold shut. So what happens if if you have a let's say cavity like this, okay, and if you are filling it from the top like this, let's say, what happens, because of again low fluidity or improper ramming, etc., this part will remain empty. Okay, so your two streams will not meet and they solidify like that only, and this is called as, this part remains empty. So this is cold shut. And sometimes you'll have slag inclusions that we already saw. I mean, this is understood, right? What happens if you are pouring very fast or something like that, slag will come and it will just be inside your uh, mold, or liquid metal, and it will solidify like that only. And then the fourth ones are metallurgical defects, such as hot tear, hot spots. So hot tear, you know uh, it was discussed, I think, in the class also, that if the rate of solidification is not uniform, uh, what happens, something like this will happen. you know Ideally it should solidify like that, because heat is uniformly taken out. But what happens, in this region there is low rate of cooling, right, because of that. And therefore what happens, at the top of this material, I mean, assuming that this is also closed, sometimes something like this forms because it gets pulled, because when it solidifies, the volume reduces, right? So therefore this part becomes empty because of the pull from the solidified part, or the heat transfer, it is more in that direction. So instead of having a full casting, you have a this thing, hot tears. Okay, so you'll have big cracks, and typically happens when you have wide range of freezing point. So alloys. Okay, and if you have like thin structures, etc., then also it can happen. And then hotspots, you already know that if rate of cooling is higher in some places and lower in some places, uh, these kind of things will happen. You know that part will be always called hotspot. It will take more time to solidify, and then some things like that happen. Okay, so that's why you need to avoid those things as much as possible. And then there are some other defects such as yeah, one more thing is there. You have this coarse grain structure defects also. Let me just see. See what happens if you have like too slow of a solidification. Uh, these things happens. No, your coarse, your uh, grain structures will become coarse, and then your strength etc. goes down. So you will not get the desired properties. So in that case, something is added. One second. Huh. It was in magnesium alloys, so you can take it as a note. Sometimes stabilizers are added. Second, I think there is one question in your assignment also. They are called as grain refiners. Grain refiners are added to non-ferrous alloys to avoid coarse grain structure. Okay, and the reason is that you know uh, if you don't do that, what happens? Uh, One second. Okay. Yeah, I mean to avoid grain structures, and if you do that, it also leads to uh, see, the reason is why don't you want coarse grains is because the coarse grained structured alloys are typically having less strength than the finer grained ones. That is first. So that is one thing. And another thing is if you have coarse grain structure, that means your cooling rates are very slow. And in that case, what happens? As I said, I just said that it may lead to the uh, hot tear etc. kind of hot tearing etc. defects can be avoided if you have instead of core grains, if you have finer grains, that means the heat transfer or the solidification is faster, and then you'll not have this kind of hot spots etc., right? And then you'll not have these metallurgical defects of hot tears. Okay, An example you can remember is they add zirconium in manganese alloys or magnesium alloys. Okay, so sometimes that is also done. Okay. One second. Yeah, so I mean, yeah, with this the discussion is over, but I'm just looking because the question has two options, uh, hot tearing and formation of coarse grain structures. So what will be the correct answer? See, the grain refiners are primarily added to the non-ferrous alloy castings to avoid the formation of coarse grain structures. So the answer should be that. But as a consequence, when you have a finer grain structure, that means uh, you know your cooling is happening faster, and in that case, it will avoid the hot tearing effects or shrinkage defects, etc. So I think the correct answer is formation of coarse grain structures. Okay. So yeah, there are some other defects like miscellaneous ones. Let me just give you 1 second. Yeah, there is something called as mismatch. You know, so mismatch is nothing but mismatch between hope and drag. Okay, so those things are there. Sometimes there is something called as flash. So extra metal along partition line. So those kinds of things are there. These are miscellaneous ones. They don't come under like some specific categories, etc. Okay, so yeah, this is more or less about the casting defects. And yeah, with that, the discussion is complete for casting defects, etc. I mean, there are many casting defects. Okay, these are not the only ones, but these are like the important ones. There are around 20, 25 casting defects, but we don't study all of them because first of all you won't remember, and in exams some are asked frequently than others. Okay, so yeah, with that we'll stop for today's class and we'll see next time. I think next time we are starting welding or let me just check because new syllabus will be starting from week 5. Yeah, I think it's metal forming. Welding will be last. Okay. Anyway, thank you for your attendance and see you in the next class.